I'll take your Lab 8 reports in the lab period today. Group A at 2 p.m., Group B at 3 p.m. I emailed you a link. Have you got a question? Okay, I emailed a link about this orifice lab, and I'd like you to watch that video. It's at most 10 minutes long, and it takes you through kind of not a very detailed familiarization with the equipment, but you'll see the equipment and you'll see it in operation, and that'll give you an idea of basically what you're there to measure today. I'm going to be providing you with I'll give everyone a piece of the graph paper that you have to put behind the pins that are going to trace the jet. And I don't expect everyone to necessarily put their paper behind there and trace it, but you can if you want. We'll have enough time, and all you're going to be measuring is you'll trace that one, and basically from that be able to find the discharge coefficient for the hole, and that's related to how much energy loss there is as water flows through an orifice. So please watch that video before lab today. I'm going to have to leave lab about 3:30, so Group B is going to be working on their own. I've got an advisory board meeting at Huntington High School for their engineering program that they've got at the high school there. So I'll have to leave, and it's important that you be familiar with the equipment before we get started. The next homework assignment is due on the 28th. You've still got a little bit of time to work on that one. It's related to Bernoulli's equation and some of the more recent things that we're going to be doing. Today we're going to look at some applications of Bernoulli's equation, starting with the stagnation tube. And this is a way of measuring the flow velocity, and it's a very simple application, and it's similar to if you had a straw, one of those kind of flexible straws where the top of the straw is able to hinge separately from the rest of it, the body. If you had an angled tube or a straw and you put it down into the flow, then there's going to be a point at which a streamline stops, because inside of the straw the water level is going to rise above the normal liquid surface to an elevation that is related to the pressure at the opening of the tube. And the pressure here at the opening of the tube is partly related to the depth, but the tube wouldn't rise if this was just stagnant water. The water inside the tube would be at the same elevation as the surrounding water surface. And so what causes the water level to go higher than the surrounding water surface, the water level inside the tube to go higher, is the fact that the opening of the tube, and we have a little zoomed in view of that opening, is there's an excess of pressure at this stagnation point. And Bernoulli's equation tells us, remember that the limitations of Bernoulli's equation is that we apply it for an inviscid fluid, meaning a fluid with no viscosity, that's incompressible along a streamline for steady flow. Now, let's say that this is water, so unfortunately it's not inviscid, but that's okay. The points at which we're going to be applying Bernoulli's equation are close enough together that there's not an abundance of energy loss, and so Bernoulli's equation is still a pretty good approximation of what's happening. What this Bernoulli's equation relationship says on the left side of the screen is that if you compare two locations before the opening at location 1 and then right where that streamline dead ends, there's some energy in the water that all of a sudden is not lost, but it's transformed. The energy that existed as velocity at 1 is transformed into additional pressure at 2. And we had a similar thing in the recent example. We worked with the nozzle that was changing diameter, and there was a differential manometer in there, and at one end of the differential manometer was the downwind end inside of the nozzle. There was a stagnation going on there too. So here, what the series of equations is going to say is that you can find the height at which the water will rise inside the tube, and that'll be related to the velocity in the water. So this is a very interesting diagnostic device for essentially finding out what's the velocity in a river. And so if you consider Bernoulli's equation at location 1 and location 2, and you'll notice that the z term isn't presented in this first form of Bernoulli's equation simply because location 1 and location 2 are on the same horizontal plane. So Z1 equals Z2. They haven't even written it in this first expression here. The other thing to notice is that rather than being written in terms of head, which is how I usually write Bernoulli's equation, this form of Bernoulli's equation is written in terms of pressure. So each one of these terms is going to have units of newtons per meter squared. And so normally I write it as P1 divided by gamma plus Z1 and so on, where each of the terms will have units of length. Here it's the same equation, just expressed in terms of pressure instead of head. Okay, so we start off with Bernoulli's equation that the pressure and elevation, not shown, and the velocity pressure at 1 is going to equal the sum of those at 2. And if we look at the difference in pressure between the 2 points, so we rearrange the equation and we know that the velocity at 2 is 0 because of the stagnation point. The water will fill up the tube, and for a very short period of time, when you first put this tube down into the water, initially the water will only be as high as the surrounding water surface, and then it'll go up, but it very quickly reaches equilibrium, and then conditions are static inside the tube, meaning that the water isn't flowing inside the tube in the same way that water is flowing past it, and the water that approaches it is flowing. But then it reaches the point of stagnation. So inside the tube, it's just the same hydrostatic equation that we've always seen. We can find the pressure at location 1 as a function of the depth. And here they're saying gamma d. That's the same thing as when we say delta H times gamma. You'll notice that d is just the dimension that they're applying to the depth below the water surface. It's a vertical depth. The pressure at 2, because of static conditions, if we consider the pressure at 2, but we're going to do the hydrostatic equation from the top of this open tube. So you'll notice that if it's in air, then the pressure at this interface is 0, and then we go down, the pressure is increasing. And so how much does it increase when we get to this elevation? The pressure inside the tube is going to be the unit weight of the liquid times d and L together. So the pressure inside the tube down here is bigger than the pressure at 1. And that's true even as we go horizontally. Remember that there's no change in pressure. Inside the tube, it's this special static environment. So if we substitute these two terms into Bernoulli's equation, and that's a way of knowing what the velocity at 1 is. You can measure the velocity just by knowing the density characteristics of the liquid and how high above the liquid surface that it rises to. And so we can simplify even further that the velocity at 1 is the square root of 2gl. Okay, so 2gl. If you know the height that the water rises, then that'll tell you the velocity at 1. So this is a simple flow measurement device, but it's only going to work in a situation where you've got the fluid you're trying to characterize the velocity is water, and you have an opportunity of making contact with the atmosphere above that. So this wouldn't work for a submarine. Like, you couldn't use this device in a submarine to find out what the velocity is, because if your submarine was 500 feet under the water, you'd have to have a 500-foot long vent to the atmosphere, and then you'd have to have someone above the water looking to see how high above the ocean surface this little L is going. And he'd have to be calling down on a radio, all right, we've got 12 inches, and then the captain would be punching in the calculator, square root of 2gl, to find out what the velocity of the submarine is. You know, obviously it's ridiculous. It wouldn't work. It wouldn't work in an airplane either, because an airplane is flying through a gas. It's not flying through a liquid. And so this has limited application. It's okay if you wanted to measure the velocity of a river, you know, and they make devices that are related to this principle to calculate if you're walking, like if you're walking parallel to, you know, if you're walking perpendicular to the flow of a river and you directed this little device into the flow, then you could measure the increased pressure and calculate the velocity from that. So stagnation tubes are interesting, but not super useful. What is super useful is a Pitot tube. And this uses the same principle, but with a little bit of an engineering twist to it. If we're smart about where we measure certain things, we can make this device, and it's useful in liquid and gases, and we don't have to have that tube all the way to the surface in order to measure pressure. So there's kind of a relationship here. If you'll remember when we talked about piezometers versus manometers, and how manometers were so much more useful than a simple piezometer would be in measuring pressure. Well, the same thing is true here when we were looking at a stagnation tube versus a Pitot tube. The Pitot tube is sort of the takeoff on the same principle, Bernoulli's effect. But if we're smart about where we measure things, then it can be a lot more useful. So here's how it works in the Pitot tube. This device, ordinarily made out of metal, has two openings in it. And the two openings are measuring the pressure at different locations. What's labeled location 1, now we're looking at like a top view. So ignore the fact that location 1 is below location 2. We're looking at this from above in this particular picture here. And so the velocity that's going to intersect location 1 is going to cause a stagnation at 1. And so the pressure at 1 is going to be abnormally high. It's going to be higher than the surrounding atmospheric pressure because of that stagnation. You know, all of the energy that existed as velocity is temporarily and at just this location being transformed into a small increase in pressure. And then what this Pitot tube does is it takes the pressure at another location so that it can be differential. So instead of making the pressure difference relative to the atmosphere, it's going to, relative to the atmosphere in an inconvenient way, like the stagnation tube was, the Pitot tube takes a sampling of the atmospheric pressure very close to the stagnation opening. And what you'll notice if you look at where these tubes lead, so follow the dot as I trace, this is sort of like a maze game that you get at McDonald's on a placemat. Okay, so watch the maze game. Here at 1, the opening goes through the center of the tube, over, and it's exiting at a location that's called the stagnation pressure tap. Stagnation doesn't sound very exciting, but it's the location where you've got a little more pressure because of that transformation of all the energy that was in velocity is causing a buildup of pressure at 1. When the streamline has to dead end, that energy has to go somewhere, and it goes into additional pressure. It's the only place it can go. So location 1 exits this Pitot tube at the stagnation pressure tap. Location 2, this is a three-dimensional object. It's sort of surrounding location 1. This is cylindrical, and so there's this open chamber surrounding location 1. And if we follow the open chamber, you'll notice that there is a tube into that open chamber called the static pressure tap. And this static pressure tap is where you're trying to measure just the normal pressure of the air without taking into account a stagnation effect. So that's why it's pointed sideways instead of immediately into the flow. If it's pointing sideways, then the streamlines just go past it. There's no stagnation like there is here when it's open to the streamlines and it's trapping some of the streamlines in the opening there. Since it's sideways, the streamlines just continue past, and so the pressure that it measures there is only whatever the atmospheric pressure happens to be at whatever elevation this is located. Now, these are used in airplanes a lot. And so as the airplane goes up through the atmosphere, obviously we know from experience that the pressure decreases as you go up in the atmosphere. And so they don't have to make a bunch of corrections for the Pitot tube as they go up and down because it's automatically measuring the difference between the front-facing stagnation tap and the side-facing static pressure tap. And so then there's a gauge that connects these two, a differential gauge. It's just a little meter, and it could be measuring pressure, but instead of instead of having the needle point to pressure in an airplane, they will write other numbers on that pressure gauge, and it'll be airspeed. And so they've done the calculations in a wind tunnel, and they've taken this thing onto real planes, and they've calibrated how much of a pressure difference accounts to what velocity. And in fact, that's what this pitot tube equation tells us, is that the difference in the piezometric pressure at location 1 and location 2 will tell you the velocity at location 2. Now, what's the velocity of air at location 1? It's 0 because of the stagnation. And so the velocity that it's measuring it's the velocity of the air that's slipping past the side of this pitot tube. Now, in real life, this is kind of like an ideal equation. This is the perfect Bernoulli's equation rearranged to solve for the velocity at 2. In real world, they're going to have to make some little calibration adjustments because there will be some energy losses as wind goes past this opening. You know, there's going to be a little bit of drag that they have to account for. And so it wouldn't be this perfect equation here in real life, but this is a good starting point for us to identify what velocity the plane is flying at using a pitot tube. So P sub z, just to remind you what P sub z stands for, piezometric pressure, P sub z, is pressure plus gamma z. And so when it says P sub z1, they're saying the pressure at location 1 plus gamma, the unit weight of the liquid, times the elevation at 1. So elevation meaning what? Relative to some datum. It doesn't matter what the datum is. You can use sea level as your datum. You could use the tip of 1 as your datum. So if this was pointed down instead of like a top view, I told you earlier that this is a top view. The pitot tube doesn't have to be flying horizontal for it to work. It still measures airspeed even if the plane is flying straight down. That would be scary, a plane flying straight down. You'll still be able to get your wind speed from the pitot tube because the P sub z, piezometric pressure, takes into account the elevation above some datum. And so P sub z2 would be P2 plus gamma Z2. And so if we said, let's have this tube, the location of 1, be our elevation datum, then piezometric pressure is going to take into account how much higher above 1 location 2 is. It's going to be like a couple of centimeters or so. Very minor. It's mostly going to be the pressure difference between the two that goes into calculating the velocity. We'll do some calculations here with pitot tubes in just a moment, but so far, do you have any questions about how pitot tubes work? All right. So let's work an example here. We've got a pressure gauge. It's just an instrument that's available, and it will measure from 0 to 1 psi. That's the only scaling that it does. It won't measure any higher than 1 psi. So it's probably a pretty fine instrument. If it was measuring from 0 to 100 psi, maybe it's not as high accuracy. But this is a high accuracy gauge that only goes up to 1 psi. So psi, of course, we know means pound of force per square inch. 1 psi is 1 pound of force per inch squared. So the question asks, with that gauge, then what's the maximum airspeed that a pitot tube could be used to quantify the airspeed with this gauge? So basically, where's the pressure going to be higher? As shown here, is the pressure going to be higher at 1 or at 2? At 1. How do we know? How do we know that in this gauge, the pressure at 1 is going to be higher than the pressure at 2? That's right. So all of the velocity energy that was there got converted into a little more pressure. And so what we're saying in this problem is let P1 equal 1 pound of force per inch squared, and let P2 equals 0 pounds of force per inch squared. Now you didn't maybe it wasn't immediately obvious to you that that's the implication of this problem statement. Sometimes the hard thing isn't Bernoulli's equation, but it's applying Bernoulli's equation to unfamiliar phraseology here. But it's saying you've got some gauge that's going to connect to the pitot tube. So what is the velocity? So the pressure differential defined this. What do we know about the velocity at 1? Okay, the velocity at 1 is 0. And apparently we're doing this in traditional units, but we want to know the airspeed eventually. We want to know it in miles per hour. When we're just doing Bernoulli's equation, what units will velocity be in when we solve it? Feet per second. So we want to know V2, originally it's going to be in feet per second, and then we're going to convert that to miles per hour. Not too big a deal. Anybody know how many feet are in a mile? Good, 5280 feet per mile, of course, obviously. What other number could it be? Just rolls off the tongue, 5280. How many square feet in an acre? 43,560, of course. Another one of those that just rolls off the tongue. 43,560 square feet per acre, obviously. How many slugs per... no, we could do this all day. All right, 5280 feet per mile, and then the other one is 3,600 seconds per hour. So when we get to that point, we'll use those conversion constants, right? Why does the problem statement say that we've got 60-degree Fahrenheit air? What does that matter? Yeah, the unit weight and the density. We've got both in this equation. Now, before we get into that, let's consider the z's. Looks like the plane is, let's assume it's flying horizontally. So we're going to let z1 and z2 equal each other. z1 equals z2, so when we actually start crunching the numbers, we'll just eliminate the z term altogether from Bernoulli's equation. Okay, so that said, we don't need the unit weight because the z's are going to cancel, but we do need the density. So we need to know the density of air in terms of traditional units. Has anyone got the textbook available today? It's in there. Appendix A. We want to know the density of air at 60 degrees Celsius. No, Fahrenheit. 60 degrees Fahrenheit. All right, mechanical properties of air, 60 degrees. Okay, we're going to want the density, and it's going to be in slugs per cubic foot. What have we got? 0.00237 slugs per cubic foot. All right. Anything else that should be a blip on our radar to solving this problem? The units. The units give the hint. That would be that's a good one to be aware of. Actually, we leave the slugs the way they are because when we put slugs in here and we multiply it by feet per second and square that, then it's going to turn into pounds per foot squared. So I'm glad that you pointed out slugs because it's always a little weird working with slugs. I mean, because we know it's obvious that a Newton is a kilogram meter per second squared, right? That's obvious. Well, the same thing is that a pound of force is a slug times a foot per second squared. So there's that same thing there. And so what we want each of these terms to be in units of pounds per foot squared, and that's what we'll get when we have slugs per cubic foot and multiply it by this second term. Okay, so that's fine. It's the pressures. What do we have to do to the pressures to get them ready to use? Yeah, right now we're in pounds per square inch, and so right now we know that pressure at 1 is going to be, in 1 square inch, 1 pound of force is going to be pushing on a square inch. But we are going to have, if it's 12 by 12, because there's 12 inches per foot, then there's going to be 144, I'll just do this, etc. 144 inches squared per foot squared. So we have to multiply the pressures by 144 in order to go from pounds per square inch into pounds per square foot. And sometimes it's hard to know, well, do you multiply or do you divide? And sometimes I just have to draw this little thing or imagine it in my mind that if you have 1 pound in a square inch, how many pounds are you going to have in a square foot? Obviously, it's going to be a lot more than that. It's going to be 144 pounds per square foot if you've got 1 in a square inch. All right. So I'd like you to jump in and start substituting and trying to find out what is V2. That's the thing we're solving here, V2. And while you're working on that, I'll go grab my notes because I left them in my office. So what we learned from this example is that you actually need a pretty sensitive pressure gauge to measure wind speed in an airplane, because even just this small 1 psi increase is turning out to represent 238 miles per hour. We eliminate the Z1 and Z2 terms from Bernoulli's equation and the V1 term because there's no velocity at 1 due to stagnation. We're left with P1 is equal to P2 plus density, velocity 2 squared divided by 2. Rearrange that to solve for the unknown velocity at 2. Substitute in our pressure difference of 144 pounds of force per square foot. And we get 348.6 feet per second. And if you multiply that by 3,600 and divide by 5,280, then that's 237.7 miles per hour. So there are some airplanes that, before they stall can fly as slow as 40 or 50 miles an hour. So you'd need to have a very sensitive pressure gauge to be able to convert an increase in pressure into a wind speed. Any questions about this first example? Well, let's consider another one. Same device, different fluid. Instead of being oriented horizontally through air, this pitot tube, as you can see, is connected to a differential manometer. We don't just have some gauge with a dial on it. Instead, we're using a differential manometer and are measuring the deflection between the two liquid surfaces in order to measure the pressure. That's the poor person's pressure gauge, I guess, is a differential manometer, and that you just measure the Y. So here, we've got it pointed into a pipeline that's carrying kerosene. And we have a manometer deflection that in the problem statement is defined as 18 centimeters is Y. And we want to know what's going to be the velocity in this pipeline. And the key to this problem is we have to write the manometer equation between 1 and 2 because we want to put that into Bernoulli's equation. This is the Bernoulli's equation as we've rearranged it when it's in terms of piezometric pressures. The interesting thing is that we aren't given how far elevation difference there is between 1 and 2. We don't know Z1 minus Z2. That information isn't provided, but it's accounted for automatically in Bernoulli's equation since there's a piezometric pressure term. All right, so let's take a look at this one. If we start with the manometer equation, we are going to begin at location 1, and we're going to work through the manometer just doing the hydrostatic equation. So it will start off with P1, and as we go down, it's going to be the rate of pressure accumulation will be the unit weight of the liquid. And this is kerosene, so it'll go down unit weight of kerosene, and the distance to the next point, we're going to go down from 1 to 2, and this is inside that center tube that we're working because the static equation will apply as long as conditions are static. Z1 minus Z2 plus gamma caro times L, where now the depth that we're going down is from location 2 to this interface here. We've got kerosene in the pitot tube and inside the manometer, except for where we have mercury as the liquid inside here. Okay, so we're now working our way down towards this surface. And our next step will be to go upward from this interface to that interface, down and then up again. So the net change is an increase, so we're subtracting pressure, and it's the unit weight of mercury, which is abbreviated Hg. And we go up the distance y to get to that next interface. And now we're going up again, so it's minus, and it's through kerosene once again. But the distance that we're going to go is from this interface up to 2. And so we don't directly have a dimension that's telling us how far it is from that interface to 2. But it's not that complicated. It's just L minus Y to get from that interface up to 2. L minus Y. And then that gets us to whatever the pressure is at location 2. So we've applied the hydrostatic equation through the manometer from 1 to 2. Even though the liquid is flowing inside the pipe, we couldn't apply the hydrostatic equation in the pipe, but inside the manometer and inside the pitot tube, conditions are static there. So it does apply. So the next step is we're going to group terms by piezometric pressure. What that means is piezometric pressure is P sub Z is P plus gamma Z. So I'm going to find all of the terms that are related to P1 and gamma Z1, put them together, and then call that P sub Z1. I'm going to gather all of the terms that say P2 plus gamma Z2 and gather them together, and I'm going to call that P sub Z2. So if I rearrange this top equation, I can rearrange it to say P1 plus gamma kerosene Z1 minus P2 plus gamma kerosene Z2 is equal to Y times gamma Hg minus gamma kerosene. So let's look here and see if I've forgotten any terms. In some cases, terms might have canceled out. For example, here we've got gamma kerosene times L. Over here is gamma kerosene times L, but it's a minus. So those two terms cancel out. That's why we don't see that in the rearranged version that I've just written on the board. We've gathered them together. So this first one is P sub Z1, and then this term is P sub Z2. Okay, so P sub Z1 minus P sub Z2 is Y gamma Hg minus gamma kerosene. Rearranging it this way probably isn't immediately obvious to you. Like if you just like put all the terms of this equation, like if they were all written on dice, you know, you rolled the dice and you threw it out on the table, it wouldn't immediately like boom, it wouldn't just like randomly be rearranged this way. But you need to get to the point to where you could do this. You know, I'm giving it to you on the board. Here I am writing it and telling you this is the solution, but you need to understand these terms and start thinking in an engineering way enough that you can come up with this sort of equation on your own. It's a, you know, it's a lot of work to get to that point where it's familiar enough and you can think, well, this is all about piezometric pressure. Maybe I should look at grouping it in terms of piezometric pressure. That's not an easy thing, but it is a necessary thing. That's the problem-solving ability you need to have. Yeah? Okay, we had plus gamma kero here and minus gamma kero here. So if you add them together, they equal 0. Other questions? All right. That's the only term that vanishes entirely. Well, no, that's not true because here, or is it? Yeah, okay. That's the only one that goes away completely. Okay, so we're done with the manometer equation for now. What we're going to do is consider the pitot tube equation. The pitot tube equation says that the velocity at 2, where 2 is that opening that's facing sideways, you can find the velocity there. It is 2 divided by the density of the fluid, P sub Z1 minus P sub Z2. And what we're talking about is the fluid is kerosene that's flowing in the pipe. So that's what we're going to have to use as the density. It is 2 divided by the density of kerosene, and then P sub Z1 minus P sub Z2, well, that's what we found on the left-hand side of the manometer equation. So instead of putting numbers in here, we're just going to substitute this other expression. We're going to take the right-hand side of this equation and drop it into the pitot tube equation. So P sub Z1 minus P sub Z2, well, that is Y times gamma Hg minus gamma of kerosene. And everything is to the 1/2 power. I should have written that over here. I forgot to. Sorry about that. See, it's to the 1/2 power. That's our pitot tube equation. So I don't know the two piezometric pressures directly, but I do know that my manometer is going to give them to me. And so that's why I've made the substitution. That's why I've dropped in this term here, where previously it was looking at the difference in the piezometric pressures. Any questions? We finally get to start substituting numbers now. Finally. Okay. If we know that mercury has a specific gravity of 13.6, the gamma Hg that we're going to use will be 13.6 times water, 9810 newtons per meter cubed. So the mercury unit weight that we're going to use, 133,416 newtons per cubic meter. The unit weight of kerosene, we are told that this kerosene has a unit weight of 0.81. So 0.81 times 9810 newtons per cubic meter, and that is 7946 newtons per cubic meter. And finally, we have to know the density of the kerosene. And so that's 0.81 times the density of water, which is 1,000 kilograms per cubic meter. And so the unit weight of kerosene will be 810 kilograms per cubic meter. So let's put those numbers in. 2 divided by 810 kilograms per cubic meter. The distance y in the problem statement tells us it's 18 centimeters, so 0.18 meters. And now the difference in the unit weights. So the difference between the 133,416 newtons per cubic meter and the 7,946 newtons per cubic meter of the kerosene, and then all of that to the 1/2 power. Okay, so it will work out to be 55.76 meters squared per second squared to the 1/2 power, which ultimately gives 7.47 meters per second as the velocity of the kerosene inside of that pipeline. All right, so lots of equations and calculator and cerebral stuff this morning. This afternoon we're going to be able to do some hands-on. Lab at 2 o'clock and 3 o'clock. We're splitting up into our normal 2 groups. What are you going to do between now and lab if you haven't already? Watch the video. Watch my YouTube video. It's not even monetized, no commercials. It's less than 10 minutes long. And once you watch it, you won't have any questions on how to do the experiment, the calculations, or even the graph. It's just all right there in under 10 minutes. So, all right, I'll see you at 2 o'clock with your lab reports. Take care.